Hello, students. This is Professor Scott Norman from Pittsburgh State University in the Department of Automotive Technology, and we are continuing our series on how does the AC system work on mobile vehicles. So this is part of our mobile climate systems class that we teach at PSU. And so we've already talked about, in the first part of the series, we talked about capillary valve TXV systems, and on the second video, we talked about the H valve systems. On the third video, we talked about the Orifice tube system, which you see right here in front of you. And then in this video today, the fourth video, we're going to talk more about Orifice tube diagnostics and the difference between a variable orifice valve and a fixed orifice valve. So if you haven't watched any of the previous videos, you're going to want to watch those first before you watch this one. So this orifice tube right here, probably the biggest problem that you have with it is, I'm going to play the animation here, is that it gets restricted. So it's the filter of the system, and so there's a screen on it, and it's fairly easy. Well, not easy, but if something's going to get restricted, this is going to be the piece of the system that would get restricted first. So a couple of things you could do to diagnose your orifice tube to make sure it's working right. Number one, when the system is running, you're going to touch the liquid line in front of the orifice tube right here, and again that should be warm to the touch, and you touch it afterwards and it should be cold to the touch. And so again, if you're not getting a pressure drop or a temperature change in that, then that is a concern. The second thing is that when I turn my AC system off, you should hear some hissing sound, and so it kind of sounds like a tire leak. But the hissing sound that you hear when you turn the system off is the pressure going from the high side to the low side, and the system is equalizing. Hopefully the system does not equalize through the compressor, because the compressor has, good sealing rings or a good seal between the piston and the cylinder walls. They don't use rings anymore like they used to in the olden days, but they use like a Teflon coating around the piston. So there should be a good seal between the piston and the cylinder wall, and the valves should be sealed. And so ideally you don't want any equalization between the high side and the low side through your compressor, but it would be through your orifice tube. So you hear this hissing sound for about, I don't know, I would say around 30 seconds. And so that's telling you that the system is equalizing. You could watch your gauges, and as the system is running, let's say your high side is at 200 psi and your low side is at 25. In that 30 seconds of equalization, you should be able to see your high side dropping down and then your low side going up until the pressure is equalized to whatever the underhood ambient temperature is. So if the underhood ambient temperature is 100 degrees under there, well, then the system should equalize where both the high side and the low side is reading around 100 degrees. And so if that doesn't do that, that's indicating, ooh, there's a problem somewhere and I need to figure out what's going on. So like if equalization happens for 5 minutes on orifice tube system, I am very concerned about that. And so again is that you're looking at equalization rates, you're listening for that hissing sound, and that helps diagnose that system. One of the things that is different between an orifice tube system and an H valve system, and I'm going to switch over to the H valve system here for a moment, and here we'll do capillary because it's easier to see, is that if there's a restriction right here in this H valve, I'll play that animation, what will happen is that, again, the high side won't necessarily build up high pressure at all. It will go, sorry, I hit the wrong button. I'm going to hit pause here to kind of show you what a restriction would look like. So, and we'll restrict it right there, boom. So it's restricted right there. If there's no notch in that or that valve, like what you see right here, there's no flow whatsoever. It's totally restricted. It's rusted up, it's corroded up, the valve can't move. Then you're going to pull a vacuum on this low side, and the high side doesn't build up a lot of pressure, maybe 120, maybe 130. But the big kicker here is that it's going to look like an undercharged condition, except that the low side is going to be extremely low into a vacuum, versus the high side would be up above 100 somewhere. Typically on a undercharged condition, if the low side pressure is down at 10 or 5 or into a vacuum, well then the high side would be way under 100. So the difference between an undercharged and a restriction for the experienced technician, you can see the difference in that gauge reading. If you're new to this, it's going to take some time to, hundreds of times looking at the gauges before you kind of like see the subtle differences between a TXV being restricted versus a undercharged condition. But the key here is that the low side is going to go down pretty darn low, almost into a vacuum, if there's no flow whatsoever. Now, if I go to the orifice tube system as a comparison, we're going to allow the refrigerant to go through, and let's say that there's a restriction in the system. Boom, right there. So that the refrigerant can't go through. What's going to happen? Well, it's a different scenario, and what's going to happen is that the compressor is going to kick on, and the pressure is going to start. We're going to start pulling a vacuum here on this low side, and when the low side gets to about 20 psi, the clutch kicks off. And as the clutch kicks off, the pressure rises slowly, and I'm going to use the word slowly back up to around 40. And then the clutch kicks back on again. And then the pressure drops quickly. The pressure is going to drop really quickly down to 20. And then the clutch kicks off again. And so what's happening is that you don't see the pressure drop down to a vacuum on a restriction on an orifice tube system. What you're seeing is you're seeing it cycle. Because again, around 20 psi, could be 18, could be 22, whatever that low pressure cutoff switch is set out at, it's going to cut the system off. And so how you identify this is the cycling that's happening. You're going to realize that the off time is more than the on time. So when the system cycles off and it's at 20 and the pressures start to try to equalize, from 20 to 30 to 32 to 35, it's happening incredibly slow. Because, we're typically trying to equalize through that orifice tube, and it's just not happening. You have a restriction. Then when the system tries to kick on, well, since you have a restriction here, it's going to drop down really quick. And so the compressor may only stay on for a few seconds before it kicks back on again. So when you're looking at that cycling rate, it's important to look at the off time versus the on time. We would, on a good system, let's say it's cycling because it's just cold outside, because there's no heat load in the evaporator. If the system is undercharged, that's also, times where the system will cycle off and on. You're looking at on time versus off time, and you want the on time to be more than the off time. If the off time is more than the on time, well, you start taking a look at equalization rates and how long that's taking, and that helps also indicate that there's a restriction. And again, then if you think there is a restriction, you're going to hopefully be able to disconnect that line. You could pull out that orifice tube and you could do a visual inspection. So that time sometimes it's nice. You can say, oh yeah, there is a restriction. And if the orifice tube is restricted, then the next question is, what's causing it to restrict? And so then it's like, hey, is the compressor coming apart on you? Is all that Teflon coating on the pistons coming off? Is there metal on that screen? Did somebody replace the compressor and did not change the condenser? We'll show the callouts here. And so at that point, the condenser, some debris from the previous repair got knocked loose, and then we're plugging up that orifice tube again. So you're going to want to look at the history of the repair to see, if someone's been replacing, one compressor, two compressors, and again, not doing a back flush or not replacing that condenser. Let's talk a little bit about this orifice tube. And so I'm going to click on this orifice tube here. And so what I have here is I have two different variations of an orifice tube. I have a fixed orifice tube, so an FOV, which is, that's a pretty standard orifice tube. And here I could play this animation here. And you can see that, the flow of refrigerant is going to go from the big side to the small side. You got this tube that's around 60 thousandths, I tell my students, so 0.060. And so there's a constant flow. There's a screen all the way around here. If you look at the orifice tube really carefully, there's an arrow, and the arrow is going to be pointing towards the direction of flow. So the arrow on the orifice tube should point to the small end. The small end right here where I'm pointing to has a piece of plastic that's like a diffuser. So as the refrigerant, that liquid refrigerant, goes through that orifice tube and it hits that diffuser, it helps kind of spray it out, is what it does, and it tries to help atomize the liquid refrigerant. So it's getting ready to evaporate as soon as it gets into the evaporator to pick up some heat. So you know, so that's pretty standard. And these tubes are not sometimes easy to get out. You know, they're special tools sometimes to pull them out. Sometimes you pull them out and they break in two, and that's terrible. You know, sometimes you're pulling it out from the short end. Sometimes you're pulling it out from the big end, just depending upon what side of the connection is the orifice tube is in. So I tell the students, you know, you can put an orifice tube in 4 different ways. You know, you could put it in this way first, or you could put it in this way first, and you have 2 different lines. You know, so you could put it in either the line that is connected to the condenser 2 different ways, or you could put it in the line that goes to the evaporator 2 different ways. And so you just want to make sure that you don't make a mistake and get this in backwards, because I have systems that I've taken apart where students have physically installed it backwards, and so I've seen it. So it can be done. So that's something to kind of pay attention to as far as which way this should go. So I want to talk a little bit about this variable orifice tube. So variable orifice tubes, I remember starting to see them on the PT Cruiser, when the PT Cruiser came out with Chrysler Corporation, and so we had to train our technicians all the time. So what's different about a variable orifice valve, and I'm going to show callouts here for a minute, is that you have 2 different paths for refrigerant to flow. So you still have a big end. You know, that's the end that's going, that's the high pressure end that's going to the condenser. You still have the small end. Here they're showing you the diffuser on that. But the difference is that you have 2 different, you have 2 different orifices. One that's fixed, and they show you down here, you know, that fixed orifice, that big one is around 47 thousandths. And then you have a variable orifice that's 15 thousandths. So it could go all the way open, like what you see right here. So if you add those 2 guys up, you're looking at around 62 thousandths of a total opening. Then what happens is that when the temperature of the liquid line on the high pressure side changes, you have a spring in here, a bimetallic spring that will rotate. And when it rotates, it opens and closes this variable orifice. So the orifice could be somewhere anywhere between 47 thousandths to 62 thousandths. So I typically ask this question to my students, and students, I will be asking you this question in the classroom, is that, let's give you 2 scenarios. So the first scenario is I'm going down the highway at 65 miles per hour. I don't have much heat load on my car in a hot summer day. How is this variable orifice valve going to work? Is it going to be all the way open, where I have a total of 62 thousandths, or is this variable orifice going to be closed, where I only have an orifice of 47 thousandths? Then, as I'm going down the highway, I hit a big traffic jam. It's a hot summer day, and now I'm in stop-and-go traffic. I don't have any good ram airflow at my condenser. Fans are on high, but again, now I have a heat load. You know, I'm not able to get rid of the heat as good as I could going down the highway. So my pressure in the system is going to start going up. So if I have a high heat load, what's going to happen is, again, am I going to have this variable orifice all the way open, or am I going to have this orifice all the way closed? And so this is, students, this is a good time to maybe pause the video and think about this. You know, so city driving versus highway driving. What's going to happen to that variable orifice? Is it going to be all the way open? Is it going to be all the way closed? That's the question I asked. So are you ready for the answer? So almost always, and the reason why I ask this is that almost always students get it wrong. And the reason why they get it wrong is that they use their knowledge of a TXV system, and they say, wow, on a TXV system, if I have a high heat load, pressure goes up on the suction line. I want to open up the system. And when I don't have a high heat load, I close the system. And so they use their knowledge of a TXV and apply it to a variable orifice valve. And they say, well, it works just the same. And no, it doesn't. It does not work the same. It works just the opposite of a TXV. So if you think about it working the opposite, that helps try to remember what's going on. So what's happening right now is that the valve is fairly open. So I have flow going through both of them, and so that would be so if I have both, you know, both variable and the fixed orifice open, so I got a total of 62 thousandths opening right there. That would be going down the highway. That would be like going down the highway with a low heat load. So think of this as just like a regular old fixed orifice valve. See, I don't need extra cooling when I'm going down the highway at 75 miles per hour. I need the extra cooling. I need better cooling when I get into that stop and go traffic where I have a really high heat load. So what happens is that when I get to a certain temperature, probably 130 or 140 degrees, on my high side pressure, my liquid line pressure, that's getting pretty high. This variable orifice, this bimetallic spring, is going to start to heat up, and then as it heat up, it rotates. And as it rotates, see my hands here, as it rotates, it's going to constrict this spring, and that valve is going to close. And as the valve closes, it's going to go to the 47,000. So it's going to go to a smaller orifice at a high heat load. And I'll play the animation down here so you can kind of watch this valve. Right now the valve is open and we get a high heat load, and there it goes. It just closed. And so what they would say is that it would close out at around 150 degrees. So at 150 degrees of liquid line temperature inside, that valve would all the way close, and then I would have only the 47,000 orifice there. Okay, so that's a high heat load. And then if I get out of the stop and go traffic, and I start going down the highway, I have lots of airflow, ram air going through the condenser. I'm able to get rid of all that heat out of the condenser. The pressure start dropping down, the temperature will start dropping down. Then it would then open back up again because there we go. So there's my my highway driving on that. So the questions are the students are a little sometimes confused on how that works. So we would tell technicians, by the way, that putting a variable orifice valve in would typically lower your city driving, high heat load type driving by about 5 degrees. And so they actually had kits where you would put you would take out your regular fixed orifice valve on, let's say, trucks, a Dodge truck that didn't cool very well, on their city driving. It did fine going down the road at a high speed. And you would put this variable orifice valve in it, and it would give you about a 5 degree difference in your duct outlet temperature. So if it was putting out 45 degree air on the best of the best hot days, well, it may drop down to 40 at that point in time. So let's just, I'm going to go ahead and I'm going to forward this back to close. So let's say that I did make a orifice tube that has 47 thousandths on there. So we're going to get it to there it goes. It just closed. So there's now my 47. So let's say, so the question is that why don't all orifice tubes then, a regular fixed orifice tube, be at 47 thousandths? Well, you start thinking about how much during the year you drive where it's a high heat load condition. Think about operating the air conditioning in March and in May and June and in the mornings and going down the highway, So most days, if you had a 47 thousandths opening, what's going to happen is that you're going to get a huge pressure drop in through your orifice tube. So what that means is that by doing that, evaporation would be happening too early in your system. You wouldn't necessarily be flooding your evaporator. That evaporation is happening too early. You start to boil your refrigerant before the evaporator and not inside the evaporator where you get all your heat transfer. And so this would only work on the hottest of days. And remember, on a orifice tube system, if you're dropping pressure too fast, it's cycling. So if I had a 47 thousandths orifice on a fixed orifice valve, I would be cycling all the time except on the hottest of the hot day, and I would be cycling too much. And so what they did is that with this variable orifice valve, they put it, and I'm going to go ahead and I'm going to forward it again, is that they made it to where it only uses the 47 thousandths. It closes off, from your normal, with the 60. So this would be normally going down the road, a low heat load. So let's say I'm operating the air conditioning on, let's say the fall months, September, October, maybe the beginning of November, it's 80 degrees Fahrenheit outside. You don't have a high heat load. By putting 62 thousandths through there, I don't get as much pressure drop. That means that the refrigerant has to travel a little bit further and get into the evaporator before it starts to really evaporate. And so the key is that I'm getting, we'll call it normal cycle time on a mild day. Maybe when the engine warms up, it doesn't cycle as much. But I don't get as much pressure drop, and that way we're evaporating the refrigerant at the right time in the evaporator. And so what's great about this system is that on those days that your evaporator can handle it, you have a high heat load, the evaporator can handle it as much, we're going to, again, and you know that because this variable orifice valve will change. And again, this design is changed with temperature. I've also seen designs in here where you have a valve inside here and it changes with pressure. So pressure, temperature, doesn't matter how the valve is designed. It can be done either way. But as the pressure goes up or as the temperature goes up, it's going to close, which is going to allow that evaporation in the evaporator to evaporate just a little sooner as that refrigerant goes into the evaporator. And again, why? Well, because the evaporator could handle it. There's enough heat load to ensure that all the refrigerant is evaporating in the evaporator, and my compressor runs continuously, and I'm not getting all types of cycling. So hopefully that makes sense to you guys. I know it's a little confusing on that, but again, think of a variable orifice valve, sometimes abbreviated VOV, versus a fixed orifice valve, an FOV, is that that it opens and closes just the opposite of a TXV. And of course, if you remember that, that would probably be the best way to figure that out. So this is Professor Scott Norman. Hopefully you enjoyed the video. If you're looking for more automotive educational videos, just subscribe to my Professor Pintang YouTube channel. Thank you very much. You guys have a good day.